speaker this evening has a very impressive 30 years of industry experience, has previously been the lead engineer of Novell. Please welcome the co-founding CTO of Aerospike, Brian Bulkowski.
Hey. Thanks for coming out tonight. So where am I supposed to stand so that I don't look funny? You told me there was a spot, right?
Yeah, there you go, you got it.
Yeah.
Now you can never move.
I can never move. Okay, we're going to talk about machine learning. So it turns out that a huge number of Aerospike folks are doing a lot of large-scale machine learning, and they're using some patterns that I think are kind of interesting. So we're going to talk about that. I am going to talk a little, just tell you for a few minutes about what Aerospike is. How many of you have either used or know Aerospike well? Not very many, so I feel like I'm not wasting your time. Excellent. We founded the company in 2009. We're a Silicon Valley-based venture-backed startup. We have about 80 employees, plus or minus. I wrote the original code myself. I had a co-founder, a guy named Gianpaolo. I have a different co-founder named Retraining. Our first customer, as was mentioned, AppNexus, not that far from here. Nielsen, also not that far from here. Tapad, I was looking at my map, is like right around the corner. So this very area right in New York and the media advertising companies have been great early customers of Aerospike for a long time. When I started the company, I thought that there was underinvestment in high-scale key-value stores. Every company that I was at that time was building their own bespoke key-value stores. They found that the ability to use RAM was always difficult, and you ended up doing sharding. Sharding took about 6 months to a year to get right. You would have a lot of production outages, but they would end up doing it themselves, usually on top of Memcache. What I saw at the time was that Flash was going to be a really interesting technology, Flash SSD storage. It was just starting to happen in 2008, 2009. What's great about it is you can go and fetch a single small piece of information randomly at very, very, very fast rates. And that bet on Flash that we made back in the fundamental data structures, it's really a very different kind of data structure than is used in any other database even to this day. What you see in systems like RocksDB, which is considered to be a very good Flash optimized database, is in fact still level-based compression. Level-based compression has this tiering system where it continually rewrites stuff, and that ends up with about 4 times as much writes as you end up having with the kind of data structure we use. So that was part of the idea, was to say, hey, let's do an entirely new data structure, which we now call hybrid memory. Now, we added something new last year, which was we added a positive Jepson report and strong consistency. And I've now spent a lot of time trying to understand what other distributed database writers think consistency and not losing write data is. And I've realized that there are a lot of holes in a lot of the systems, which is part of what the Jepson guys find out too, right? So Mongo's done a great job in not losing data, working with Kyle, going through the Jepson test suites. We have now too. It was a 2-year-long project to get our distributed system tight enough that can be used for true high performance, but also perfectly accurate transaction processing. So we're currently in a trial that's going to launch in about 4 weeks in Europe of a large-scale transaction system. We're used, I think, in every Indian transactions processing company except the one run by the federal government. So all of the public ones, Phone PE, ATM, etc. And a lot of that was because of this new strong consistency work we did. We have spent a lot of time over the last few years putting in a lot of enterprise-grade features. We have a very strong security suite. We also have document indexing, so basically multi-model data structures. And some of those end up being really key for the kind of the use cases we're going to talk about today with machine learning and AI. So who ends up using Aerospike and what do they end up replacing? You can read the slide yourself, and we're going to talk about fraud detection a lot today. What I like to say, and I said when we founded the company, is wherever there's money, there's fraud. So people who have fraud have money to spend on databases. It's a really nice, happy coincidence as a business person. We've also had a lot of use within telcos. There's a lot of relatively small but very high density but also high availability use cases in different telcos. One of our largest ones is Airtel out of India, a fairly large phone company, 3rd largest in the world. The other 2 are Chinese. And they've standardized on Aerospike for all their key value uses. This is the end of the product slide. We're going to talk about AI in one more second. So I mentioned Cassandra. Cassandra, we often replace a lot of that. It's not a very efficient database. Its claim to scale. Even systems like ScyllaDB are still using things like level compaction. They can't use Flash as fast and as accurately as we do. Compared to the clustering that was put in Redis is a little bit of a mixed bag, right? There was Salvatore said one thing, the Redis Labs guys said another, and things got a little crazy in there. We do a huge amount of our business in public clouds. Probably at least half of our paid deployments of our 150 customers are in public clouds. Because what do you want in a public cloud? You want the ability to snap in new servers really quickly and basically take on new load, etc. So it works great in the public clouds. We have great working relationships with Amazon, Azure, and Google in particular because we're in Mountain View and they're in Mountain View, and a bunch of my friends are there. We also now have one of the largest, I believe the single largest user of Google Compute Engine uses Aerospike. So it's some pretty staggering levels of scale. Okay, let's talk about AI. Thank you for listening to me about the product stuff. And we can do some Q&A on it either, but I want to get to the fun part of the talk. One more thing. The one thing you want to remember about Aerospike is we are open source. So not every feature is in open source, but you can download it this afternoon, this evening, go home, download it, get the Docker container off of docker.io, fire up a cluster. You can go over to Amazon or Google. We're in all the marketplaces. Just fire yourself up a cluster. It should take you less than an hour. I've gotten a whole bunch of people who say, oh yeah, I downloaded it. This was easier than most other databases we've ever found. And boy, then I could actually see the failover characteristics, etc. So if you don't believe our performance claims, they're a little bold. You go to the website, you go, I don't know, this looks like a bunch of marketing. My marketing guys aren't here, thank God. Okay, the point is that's why we did open source in 2014 was we realized that people didn't believe our claims. So just go and try it. If you need a RAM-based data source, you need, even if you need a small-scale system, you're looking for something better than Memcache that's fully clustered, just try using Airspike. It's open source. Okay, what's this AI pattern? We came up with a clever name, Hungry AI. That was my marketing people doing a good job. And here's the basic idea behind this AI pattern that we've been seeing. This is a lousy slide. So the key to what they're doing is there's a computational pattern in AI that says, let's move the data as close as possible to something like a GPU and only operate on a few gigabytes of data, right? And so most of the frameworks, especially Google's framework, really make a point of doing that, where you've got a compute and you've got your model and then you've got a small amount of data, which works great for image recognition, right? Because you've only got one image, you load it in, you've got a certain amount of patterns, you have a small number of images. However, when you're dealing with large data sets like fraud detection and advertising, what you need is every scrap of available data to be available to every CPU all the time. Every scrap of data. So instead of localizing the data to a CPU and having fast access, what I will show you is the folks who are doing AI at scale are making a huge amount of data available, essentially as key value stores. And the case, and a great example, just to fix it in your mind, is an IP address. There's only 4 billion plus or minus IP addresses, right? So that's what we would call, at Aerospike, call a fairly small data set. If you take every single flow out of every single IP address that you can see, if you're let's say a payments provider like PayPal, you see a lot of the internet. And you see a lot of flows, and you see a lot of timing information on each one of those flows. So basically that's a stack of events. Use our map interface, you get a timestamp. It also allows you to do things like backtesting and simulation really, really rapidly, so you can get an individual date time. But you can basically stack up those events. So then you've got all of that data available. That's probably me. All of that data is available to every CPU. And that's what I'm calling Hungry AI, and I'm going to take you through a bunch of the cases. So you see a lot of this stuff like this particular analyst said it's all about distributed in-memory processing. Well, in a sense, but what we see for at-scale stuff is there's a network hop there. So you're not doing it on one machine in RAM, with all of that information. You're doing it with a shared data store that is simple and fast, and then you have a separate compute layer. So where is this happening in ML? You know, I'm going to skip through these slides. Okay. So what are the components that makes this pattern work? If you have all of that data available all at once, you can do, first of all, online model updates. And by online, of course, I mean in real time, moment by moment, as data is changing. One of the other talks I was here with Eric, we actually had the folks from Exalate, which was around the corner, and he actually talked about exactly how he does this in production. That was a couple of years ago. And so what he said is that they take a separate model for every ad campaign. So every time someone, an advertiser comes in and says, I have a new campaign, I want to run it, they run a seed set, and then that runs for about 3 or 4 days until they get a nice, well-trained model, and then they are updating that model moment by moment. So they're actually doing model recompute on a second granular basis, which is kind of crazy, right? Most people, they take their models and they compute them on the back end in their data lakes or HDFS style systems, and then they take that model and then they push it over to the front edge. That's not what these guys are doing. They're doing full retraining. What online retraining actually gets you is much better multi-layer deep learning as well. Because what happens is the models, when they end up updating, they're updating in synchrony. So if you get, for example, a categorization error at a lower level, or overspecification getting fixed at one level and being properly specified, then the separate layers of the model will end up learning that and improving right now, not the next time you move your models over. So instead of having your models continually be behind and having basically slower training times in multi-layer models, you end up having a much tighter and more effective system with multi-layer models. Sir.
So is the data set static, or does it keep updating?
Keeps on updating.
So he's getting more data.
Yeah. This is what online. So online, right? So what that means is, let's imagine that you are a large ad network. You've got a ton of data, right? You see every pixel. You've got partner networks coming in. You've got all these cookies. You have a huge amount of behavior. You don't just have clicks. You have search terms. You have every web view. You may have interstitial movement. All of that stuff. It's happening in real time. The ad networks tend to currently run at about 10 billion to 20 billion objects. What we call, small data sets these days. The fraud detection guys have a lot more. And so that's updating moment by moment, right? Everyone's on the internet, they're doing things, and so that data set is changing. You get a new event. Person went to this site and did a search. Bam, that comes in right now. So each one of those data sets is changing. And so the way to think about it is those end up being your vectors. Right? So what happens when you're actually building and running your models is the models end up doing things like going and fetching a set of features because you've got a meta optimizer. We're going to talk about automatic feature selection a little bit. You've got a meta optimizer that's doing automatic feature reweighting, again in real time. Because it depends how well the models are performing, which features are going to be more effective. This is why doing all of this stuff online, on the front edge, moment-by-moment recalculation actually works. It is far more effective than back-end recomputation for the cases I'm going to show you and the folks that are doing it. So yeah, online. It's a pretty amazing idea, right? It's a little more advanced than folks have been doing. And so I guess here's the slide that answers that question. Is the next one. So, people talk about having petabytes in their offline store, right? That's where you're going to be doing some of your retraining. You're going to be finding some of your models back there. The folks I talk to, they say that usually, so like the Nielsen guy said, half of his models perform just fine if he does them offline. Half of them get a boost when they're being done online moment by moment. The problem is he doesn't know which half. So he has to do them all on the closer to the front edge, right? So the other thing I'll mention here is that monitoring your models ends up being key. Because what can happen is, if you have a bad data problem, a new kind of data uncleanliness that has crept into your data source, if you are using online retraining, your model will go bad very, very quickly. At that point, you need to pull back an old model. So if you use the process where you're doing exactly what these guys are doing and you're continually rerunning your models, you have to monitor for poor performance. That is usually a data sufficiency or a data ingest or a lack of data cleanliness on the front edge. And you're going to go find it and you're going to go fix it, and it's probably going to take you a day or two to figure out which one of the data sources is bad. Right when you figure that out and get your data source problem ironed out, you need to bring back your old models that hadn't gone through this, these few hours or possibly few days of poor training. Right? So that means you're going to, if you use this online retraining, you have to keep all the models for a fairly long period of time. Keep hourly checkpoints, keep minute-by-minute checkpoints, and have basically performance graphs so that you can skip back. Now, I don't know anyone doing that with AI, and that's one of the things I love about AI is because you say, well, there's a problem, which is to say, you look at your performance dips. Oh, great, so that's another model. We look for the performance dip. Once we see it come back up, then that's a signal processing problem. We're going to use AI to solve it. So it's always, get another model fixing another problem in someone else's model. So the idea here then is it's all about using this direct user experience and using millisecond grade data services underneath this kind of very large key value oriented data pool in order to do this kind of system. So this is a lot about what we're talking about with online learning. I think this is actually from a presentation that was given at Nielsen X8's Big Data Conference in Israel. I always like going there and talking. They, of course, do a great amount of it. I'm sure a lot of you folks work with some Israeli teams in this area. And so this is their idea of when they were doing batch learning, they had to build a fairly complex system that, you probably, those of you who do this, you know about it. You end up having this large-scale system. It's a fairly slow data store. It's a fairly cheap data store. It's larger. It's your research training set. Things take hours to recalculate before you can put them on the front edge. So you end up having to do a fair amount of this data pipeline. And then you end up also having this online system. And so the folks at X8 basically said, if you're going to build two data pipelines, that's really annoying. And so if you're going to build one, build the online one. Because like I said, they found that half of their models performed better online anyway. So why really bother doing as much on the batch and offline side? One question I always get asked is, okay, Brian, so
this is really annoying. I think I know how to fix this.
I'll see if that works. Okay, so if I want to get started doing this, what frameworks support the kind of model that you're talking about? Because I don't want to have to roll my own. I'm sorry, I don't have a great answer for you. It turns out that all of the cases I'm going to talk about, every single one of my customers rolled their own systems to do this, 100% of them. And I keep walking around and I say, well, okay, you're doing large-scale machine learning. Tell me about your voyage. And I went to one of them and they said, well, we used H2O.ai. We loved the workbooks. It got us started to a certain level. And then we tried to throw it at all of the IP flows known to, on the internet. And it just doesn't scale to that level. But that's okay. What we did was we knew enough then about the models we were using, the number of features that were most effective. We then basically pulled out some of the model code. In that case, they were using L1 gradient descent, so they got an L1 gradient descent library. They pulled that out, and then really you've just got a bunch of streaming events that you're working on. You run your model, and you just write a little bit of code to do that. It's not that hard. But I can't tell you anyone. I keep asking. Someone's going to say someday, this is the framework we used. But so far, everyone ends up doing it themselves, and they tell me it's just not that hard for this kind of online stuff. Now that being said, we have at Aerospike decided to try to work with as many frameworks as we can to try to make this easier, and we integrated with Spark. So we have a really nice Spark integration out there now, and it does something kind of interesting, which is Spark has this problem where joins that cut across the shard pattern that you have for clustering are really, really, really slow. really abysmally slow, right? So the Spark, when it's actually accumulating in RAM, it's sharded, the computation is sharded across its system. Using that shard pattern, Spark goes really fast and it's super nice and everyone likes it. The problem is when you have to then accumulate or join against something like a user table that has a different set of data and a different shard pattern. If you're doing that, basically doing just a join operation in Spark SQL, things go really south really fast. So what we propose is that Aerospike, being a primary key focused database, is a really great target for that join table. So do all the Spark processing you have today, but when you need to do a join like that, pull out a great key value store database, pull out our Spark connector, put that table in Aerospike, and you can even share it, right? You'll often have cases where you have a whole bunch of different computations running in Spark at the same time that need to access the same core data store. Instead of keeping it in RAM on all of those computational nodes, keep it in a shared database. That predicates on having a database that's fast enough to keep up with a large Spark cluster, and that's why you need something with this level of performance. Okay, so how large do these projects get? Let me throw some numbers at you about what's practical. So this is one particular case. I think that is a transaction processing system, one of the world's larger ones. And so, I didn't fix it, sorry. They ended up with basically 20 SATA drives, 20 flash SATA drives that I think 1.6 terabytes per physical machine. So they're running on bare metal, not the cloud. All this stuff is different in the cloud. And they ended up with only a 30-node cluster. Each one of those machines today would cost you about $30,000. So this is $1 million worth of hardware, don't get me wrong. On the other hand, it is a ton of data, right? It's 130 billion objects across the cluster. You're going to be able to do the kind of batch reads that you need to do that with a few thousand elements in the batch read and do the entire batch in 99% sub-millisecond, which is fine for a lot of these systems because the computational phase is also probably going to take you about 10 milliseconds also. So this isn't the kind of trading system that's all in RAM where you're going to be using KDB for it. This is the kind of system where it's going to be millisecond oriented and it's going to be hundreds of terabytes. But $1 million for a large scale project like this that's safeguarding your business may be a very practical use. Now, as I mentioned about latency, one of the keys to this form of AI is you end up basically needing to run the model with a particular set of data, which means doing a batch read, getting all of the responses. This kind of AI is not amenable to partial computation techniques. So you can't just do it asynchronous and you get one data point, you get another data point, you get another data point, and if one of them is an outlier, two of them are an outlier, they come back slowly and those requests took 10 milliseconds, you just get around to them later. What you really need to do running these models is you need to get all of the data at once. Now, if you're running multiple models, you may go to one model and say, what's my feature set right now and what are my weights? And then you have to go to each one of those models. Each one of those goes out and gets 1,000 data points, et cetera, in parallel. If you're touching that much data, which you can do, you need a system that has low latency across those kinds of requests and is doing things like satisfying 1,000-element key value lookups sub-millisecond. So latency ends up being a latency in the millisecond range, and predictable latency in getting things like really good 99.5 rates really matter for this use case. So those guys were also using, they had actually a smaller data set. They only had 20 nodes in their cluster, and they were running, that's also a fraud detection case. And I have some more detailed slides on that. The third hardware case is Nielsen Exalate. They shared with me their numbers. They were using older SATA drives also. They've since upgraded to some faster NVMe drives. They were also putting about 10 tera of flash per server, but then ending up with only about 10 node clusters. So these kinds of systems are practical. The hardware isn't super cheap, and you can do all of this on Amazon. Right now, we've seen some really good results out of Google's Skylake instances. They just did appears to be an upgrade to their firmware on their NVMe instances, and they got about a 10x improvement on our benchmarks, especially revolving around latency. So we're excited about that. The new C5D instances on Amazon are also performing really, really well. They're great for, I would say, modest density data sets like this. They're not quite as big, but the C5D, M5Ds with the local NVMe have been performing very, very well in their tests as well. Okay, let's actually try to walk through a couple of these real-world use cases. ThreatMetrix is a company that does digital identity. If you're in financial services, you may be a customer of theirs, and thus you're using AirSpike. I usually have a whole list of these things. Oh, you don't know you use AirSpike. Have you ever launched a PlayStation 4 game? If you have, PlayStation 4's authentication system is all run out of AirSpike. If AirSpike was to go down, people couldn't be able to authenticate to the PlayStation network. So if you call a cab using Ola cabs in India, you've used AirSpike. They do all their cab routing throughout all of India using AirSpike clusters. And they've told us if AirSpike goes down, we can't route any cabs in all of India. So this is one of those cases where so what does ThreatMetrix do? Digital identity. So what they do is they have a huge number of data sources, including proprietary. That's one of the things that they do, is they allow individual companies that have their own data sets to pour their own data sets into ThreatMetrix, and then ThreatMetrix will combine that with the publicly accessible data sets and their own secret sauce algorithms to give you a picture of whether a particular user or cookie essentially is who they say they are and to what level of accuracy. That's their business. So this is essentially a fraud detection style use case in the same sense as I was talking about, and they use AI for that. Now, the first database they reached for when doing this kind of pattern was Cassandra, because they knew that they needed a high level of scale to be able to pull this stuff off. However, their latency numbers were really pretty high, and their models and refresh times that I was talking about were really struggling. This is, again, from one of their slides. But basically, they have this problem where they do have a customer calls in, and then calling in, of course, I mean, there's an API call from a customer site that comes into their data center, and their data center then has to respond and say, is this particular cookie, this particular activity, is it likely or unlikely given the past history of this individual user? And they need to, their SLA to their users is about 100 milliseconds. Which is pretty reasonable, right? 100 milliseconds is user visible time. You know, things start feeling laggy at 150. So they want to get their, they've signed contracts saying that they need to get their responses back in that amount of time. And they're going to return back hundreds of attributes in order to make that computation. They use things like fingerprints from browser IDs, right? So if, there's a subtle change in, this IP address usually has these 5 browsers, and now there's some subtle changes to the fingerprints. Maybe that's an indication of fraud. It might be that you bought a new monitor, that's fine. But it might be that, in fact, there's something fishy going on. This is how Nielsen Exelate runs their system. So they highlight basically some of the automatic feature selection that they do, which uses AI and ML. So their classifiers are all in the front end. They've got all the different kinds of data coming in, like I was talking about, basic web activity, internet activity. And then they've got a set of models. One model, in this case, per ad campaign, they found is effective. And however, when they're recalculating it, they do exactly this automatic feature selection. I would say that the rule of thumb that I've seen so far is people start with probably 10 to 20 features. Out of the thousands that they have available. They'll often compute on their back-end systems what they think those original features will be. However, they want to have the flexibility to be able to add and remove features over time as their research improves. So 10 to 20 seems to be the number that a lot of people are starting with. It seems kind of low to me, but people are talking about, and they have 100 features available, but they're often starting with 10 to 20. They also, of course, have data cleaning. That's a big part of the AI pipeline. That sits about there. Has to sit in front of the feature selection system, of course. Their system for data cleaning, I believe, is a bit more manual, which is common, I would say, these days, common among the people I talk to. It's hard to have an AI system to do cleaning, feeding into another AI system. You tend to use heuristics and for that kind of system. And this was their idea of basically once you do online learning, you have to have the model store. They tried to use S3 as their initial model store. Their model size is about 5 megabytes. Most people I've talked to are running models probably closer to the 25 megabyte range. For the basically the matrices that they're running and storing. And so you need to be able to, when you do a recompute, you basically drop into a something like the Kafka pipeline. Hey, this particular model has recomputed, and then you have all of your compute nodes that are actually running that model. They have a freshness, and the next time they come around and need to do a calculation, they're going to go back to their data store like S3 and pull back out their new model. So you actually need if you're going to do this with, say, several thousand compute nodes on the front edge as your model runners, you end up pulling in, your model store itself ends up being a fairly serious database problem. So since they already had AirSpike for their data store, and you can see the kind of numbers they run for that, and the kind of rough hardware they use for that, they found that running their model store also on AirSpike, given that they would have 2,000 nodes, going out and pulling in a 5 megabyte object all at the same time when they did a recompute, they found that to be a pretty effective solution. So let's talk about payments-oriented fraud. It's really the same pattern, but just to make it real that there are folks out there doing this kind of large-scale fraud detection that you are using every day in payment systems. One of the keys to payments these days is dealing with effectively and efficiently with smaller and smaller payment amounts, essentially micropayments, or what we used to call micropayments. I think now we just call payments. You need to be able to efficiently be able to handle a $1 to $2 transaction without taking a huge amount of resources. So these guys are running fairly, I would say, modestly sized clusters. They only have about 150 tera as part of this online system. And it does involve both AI and non-AI systems. So the overall payment, of course, is handled with relational databases. So that was built about 10, 15 years ago, before NoSQL systems like ours had the kind of reliability that allowed you to make sense. And they have both basically prescriptive rules, which are sort of more standard data science-y rules created usually in either SQL or NoSQL. But then they also have basically a ML and compute layer that is also contributing to the fraud score itself. All of that has to sit on top of the data tier, just like I was saying. This is taken from a presentation that they did at our user conference. I think they did not allow us in the end to post that to their website. So if you want to hear some really great presentations on this kind of stuff, come to our next user summit. Or maybe we'll get it on our website. But this is a real world system. It's online today. These guys are finding that speed is often the key because a new threat will come online and they'll have an idea that they found an exploit. And usually what they do is, what the bad guys do, is they sort of probe for exploits. They look for little edge cases where they can submit multiple transactions against the same account and actually succeed and basically overdraw accounts if they do it fast enough. And you can sort of do probes, and then you're going to come through and basically do the heist and jam all the transactions in at the same time. So being able to notice those patterns when they're forming, to be able to have the online system be able to pick that up and foil the attacker right as it's happening, that's a key to them. They said that the amount of fraud that they detect is more than the entire run rate of the company. So if they stopped doing fraud detection, they would be bankrupt in 6 months. They simply, they don't have, that's how much money they would lose in this system. Identity services, a company called Newstar. They used to handle basically call routing for the US telco network. Has also gotten into a lot of other businesses, including the kind of identity-based systems that I mentioned with threat metrics. So again, it is trying to figure out who's who based on a lot of behavior. What these guys are also doing is, they're doing fairly standard, I need to track all the people. I've got 11 billion data set updates per day, which is kind of modest by ad tech standards, right? Those of you in the ad tech industry, you're dealing with 150 to 200 billion objects per day, updates per day. So, we consider this to be a fairly low scale system, but interesting nonetheless. This is their awful slide. Sorry about the colors. But essentially, it does show you the same kind of model, right? So you've got this what they call the edge database. That is the same data layer that we're talking about. So they have their machine learning system that's sitting there. It's doing scoring, classification, and modeling. This is the analytics database is running certain kinds of sort of large-scale column-oriented queries. So they find that doing those large-scale column-oriented queries in parallel to the standard machine learning algorithms, getting counters that are already rolled up counters, is a really effective thing in their system. I haven't seen that in any other architecture, which is one of the reasons why I wanted to put that in there. So they do those queries. Those queries are changing over time. I'm not sure which database technology they use there. I honestly didn't ask. But most of the ad tech guys that I talk to use Vertica very heavily for that use case and find it to be incredibly effective. These days, I think one would also nominate Snowflake for that kind of system. Excellent system for that kind of thing. But then you've got your analytics database in parallel to the actual user data store next to it. Good. So that is what I've been learning about machine learning in the wild at high scale. And that's what I wanted to present to you today. Any questions?
Yeah, you mentioned ScyllaDB.
Yes.
And in the context of that Nexus, I believe they were using Scylla for a while. They did a lot of work on pinning processes to a certain CPU so that they would reduce cache misses.
Absolutely.
Is that the sort of thing that you're doing, or you're just
Absolutely.
taking care of it by more efficiently using the SSD?
Oh, no. You got to solve all the problems, it turns out. And I do have respect for the Scylla guys. They've done a lot of hardcore systems engineering C code, just like we have. So yes, absolutely, you need to be NUMA aware, you need to be doing cache pinning, you need to know where your interrupts are. With doing storage, it's also kind of hard because storage will often be attached to a particular socket, and then your memory is in a different socket, and then the NIC traffic is possibly coming in from somewhere completely different. So getting all that stuff blended correctly, we have a NUMA aware mode, we have CPU pinning also. It's a fairly critical feature to have as well.
What sort of OS do you run on to get the best performance? Are you bypassing going directly to the SSDs, or is there a file system?
And the question is, what OS features do we use? So the approach that we took when writing Aerospike was to use as few OS features as possible. And this was back in 08, 09, when Linux was not bad, but not great. So it had come a long, long way from its original days. But also, I didn't want to have to write every driver under the sun. And I certainly didn't want to be specific on individual pieces of hardware. The cloud was forming. There was already cloud instances out there. I didn't want to have to minimize us, so we would only run on bare metal hardware. So the way we see storage is it's a block device. So we go straight to the block layer. That works great for us. I've got customers running on all-flash SANs. We punish those all-flash SANs pretty well. We push them to their limits. But they do okay. As long as we have block devices. And then we have our own data layout underneath. The hybrid memory system that I mentioned before says the best use of flash uses indexes and RAM. That gets you enough parallelism to push flash drives, because the trick with flash drives is you need a lot of parallelism. Known in the flash industry and storage as QDEF. So if you can keep your QDEFs up, if you're doing literally one I/O per read, if you have an effective cache strategy. Aerospike used to not do as much caching. We have a recently written cache. We've also implemented just recently a recently read cache as well that's independent from our disk defragmentation system, etc. But we're not really dependent on cache. And that was one of the things that in my Scylla testing, we found that they kind of needed about a 90 to 95% RAM hit rate. And we typically see in the field about a 40% RAM hit rate, which is a big difference. Sure.
I'm not a computer science or a background guy. I'm more of a front-end modeling guy.
Front-end modeling guy.
My question for you is, I pivoted over into the spatial world, and is Aerospike, which I never heard of, does it handle spatial data? Like if you want to do complex location analytics?
Yes. Aerospike does have a geospatial interface. So it handles basically GeoJSON, just like you would in MongoDB. You can create rectangles and polygons. You can say, find me all of the things within a bounding box, et cetera, et cetera.
Okay, so that's part of the show.
Part of the show. Sir.
Yeah, so I'm interested in, you talked about optimization for flash drives. So can you talk a little bit about any special data structures that you're using for indexing that are, you know,
Sure.
different from traditional ones? And I'm also interested in the GeoJSON. Do you have special geo indexes?
So I'll mention the geo indexes first, just because we talked about it a second ago. Google's S2 library is amazing, right? So that's what everyone uses, what Mongo uses, pretty much everyone uses. And what Google did with S2 is it created a Hilbert curve in terms of taking basically the sphere that we all live on. That's kind of the sphere. And you take the sphere and you project it out to a cube. Once you have a cube, you have 3 dimensions. And essentially what you do is you have these levels, and that's the larger and then smaller blocks, and then you interleave them. You end up with a hash key, which ends up being basically, you know, where a key value is stored. So once you end up with hash keys and hash codes, then you've got to deal with these layering problems where, you know, and range queries. So we do range queries only on what we call secondary indexes, which is to say columns. So if you've got a column in the data in Aerospike, then you can create an index on it. You say that's a geospatial index, and then we will basically compute those polygons and hash codes based on that, and then you'll be able to do those range queries on the individual hash codes. That's the rough way we do it. Regarding our flash-oriented data structure, where we ended up with recently was we started out with, first of all, we needed to partition data. Think of it as micro shards within the entire cluster. So an individual client node knows how to find an individual key in the key value by primary key. So we don't have any proxies. So that whole proxy bottleneck, set up your proxies, all that kind of stuff just doesn't exist. It goes direct. Once you get to an individual partition, then, and you know what server it's on, maybe the client made a mistake and it had to forward, okay, that happens sometimes, not in a stable cluster. Once you find that particular partition, so think of that as a hash map, right? So your first layer is a hash function, you've got a primary key, you apply the hash function on it, you get your partition ID, you go to that right server, you say, you know, I'm talking about partition 2. The next layer down is what we call sprigs, that's also a hash table. So that allows you to then avoid, but on the other hand, if it's hash tables all the way down, hash tables have a lot of problems too. You have the collision problem, you have the inefficiency of large hash tables. A lot of people, you know, have talked about cliff-clicks algorithms. We ended up not really liking them. I think they're very cache unfriendly. So we ended up with a red-black tree, basically on the farthest end down. So it's a hash, and a red-black tree. We found red-black trees are pretty amazing. You don't think of them that much. They're an old data structure. But Memcache was great, right? Memcache is well known as being one of the most reliable systems for in-memory data stores, and it has a red-black tree. So we took a look at the exact cache performance of that and how they got there, and the big takeaway was fixed size elements in that key. And so once you have fixed size elements, you remove a lot of the allocator problems from that index. It gives you more parallelism, and red blacks don't have a lot of rebalancing when used with random data, which is in fact what you end up having with hash keys. So once you get that element in the system, that's all cache line aligned. So it's exactly 64 bytes of metadata, Intel cache line aligned, I should say. And one cache line. Once we get that, then we can decide, is it in cache, in which case we can go look at a piece of RAM, is it in storage, in which case we'll have to go get it, et cetera, et cetera.
And are these features available in your open source version?
Yep. Go read the code. All the, you know, that kind of stuff we couldn't have, you know, just in one. Our clustering system is also, I could go on about that, and I have at other meetups here. That's also entirely the same. What we have in the Enterprise Edition is some scalability things. So cluster size limit is 8 nodes in the open source edition. If you find the one spot in the source code, you can make it as many as you want. That's, you know, not prohibited by the open source license. Sir, you've been patient.
Yeah, so in the beginning, you were talking about this sort of like continuous training.
Yes.
You're saying that that's not typical, or is this something that's newer? Or
I found it, I still find it in maybe fewer than half of the customers that use AirSpike for machine learning. Most of the, when I show up at conferences and listen to other people talk, they don't tend to talk about that as much. The TensorFlow guys love it. They're all about online.
so yeah, I mean that's too. I mean as if machine learning in a browser becomes more powerful over time, I mean, is that something that, have you ever seen any customers use that? Like, it only came out 6 months ago, but like TensorFlow.js. I mean, I don't know why in my head it just seems like the continuous training and ML in the browser.
Yeah, so the question about browser-based ML. I haven't seen people doing that.
Okay. I didn't think
because
so.
of this focus in my customer base of backend, because we're backend data, they don't talk to us about that problem. So they might be doing it. They might be doing some, say, front-end filters, and have those filters be driven, because sometimes you want to have basically a filter on the data you're ingesting back, and have that be fairly sophisticated. So, sorry, I don't know.
Oh.
Sir?
So in the traditional database application world, like we have a problem where we have to join company name to company name to databases of hundreds of millions of rows. Is there a fuzzy component to your data that you can do Cartesian joining in a very, very fast manner?
Yeah, we're not good at joins.
Okay.
We don't do joins internally, but we are really good at batch requests. And so if you end up writing your own code, and this is sort of a NoSQL thing, right? NoSQL will just say, getting the, having a key that has a list in it, and then fetching that into your application, and turning around and making that second request in the application really isn't that hard. And so that's the NoSQL answer. When we started Aerospike, NoSQL didn't really exist. We were at the first NoSQL conference, which was in Atlanta, and Mongo was there, and Jonathan Ellis was right when he was forming data stacks. So we wanted to build a primary key-oriented database and not really worry about the join problem. Because when you're dealing with internet scale and you're dealing with millions of requests a second, you kind of can't do joins anyway. And so that was the problem set we attacked to a great extent. However, I look forward to the day we do joins. We should get to it in a few years. Okay. Sir.
Hi Brian, so currently I'm working on a multi-class classification model. So the problem is that the data set has around 1,500 different target variables. So how do I deal with such many target variables?
The question is, how do you deal with, say, 1,500 target variables? Yeah. And if you were in Cassandra, given the fact that Cassandra allows you to have rows of truly infinite numbers of variables, you can pretty much do whatever you want. With Aerospike, you end up using a map. So think of us as a data structure server or a document server. So you're going to have this document, and then you're going to have each one of those variables in one row. Or you're going to need some other way to basically take each one of those variables and separate them out into an individual, think of it as an event. So instead of having an event with 1,500 different variables in it, you may end up naturally being able to find in your data source this particular event on this particular sensor at this particular value, and you end up having all of those things stream in. That's the kind of pattern I'm seeing, but I don't know if it's correct for your data set. Does that give you any thoughts?
Like usually, if I run a basic classification model like random forest or extra tree classifier, it can handle max to max like 40 different classes. So, how do I handle like 1,500 classes?
So the question is, so you're running basically one of these frameworks that's limiting you at 40.
Yeah.
So I wish I had the answer for you, and which is which frameworks out there should we, as Aerospike, be integrating with, and be able to take them to the next level. The folks that I've been talking about here that I go talk to as CTO, they all wrote their own code. So they took the random forest library and they just wrote some code around it, and they did it all themselves because they had a big enough problem and enough money to do so. So I wish I could tell you which framework are you using?
Framework as in
like are you using H2O, or are you using Spark, or are you using, you open a workbook, you put in these models, right?
Yeah, so we are using, I'm not using a framework, like just normally.
Okay. Anyway, so I don't really have a good answer for you, I'm sorry. Okay, well, we're getting on to 8 o'clock and I'm getting warm. So I think we have our drawing here. You
Yeah,
ready for the drawing, Eric?
I just passed around the bowl one more time. Did everybody have a chance to put your card in to win the Apple Watch? If not, now's your time. Where's the bowl? Right behind you. Oh, need it back to the front already. That was quick. Okay.
So thank you.
Thank you. Thank you, Brian Bulkowsi. All right, you got 30 seconds. Anyone else coming up? That's it? No? Okay, so oh, I see a card? No, you work for me. You can't do that. That's cute, though. Can I ask you to mix it all up? That's okay. Whatever it is, it is. There we go. Okay. Can I pick on you again and ask you to look that way and reach in and pull out a card?
You can lift it up above your eyes, too.
Okay, read out the card.
It's
Lynn Tran? Are you here? Yes, congratulations, Colin. Brian will be here for relevant questions right now.